You know, electricity is everywhere, right? It powers, well, pretty much everything. But because you can't actually see it, it can feel a little bit like magic. So in the next few minutes, we're going to pull back the curtain and break down the simple ideas behind this incredible invisible force. And we'll start with a question.
So, what's the connection? It's electricity, of course. A lightning bolt is just this massive, wild, totally uncontrolled burst of electrical energy. Your phone, on the other hand, uses a tiny, super precisely controlled little flow of it. They're basically two sides of the very same coin, and we're about to see exactly how this invisible force really works.
Okay, to really get our heads around these invisible concepts, we're going to use a super simple analogy. Just picture electricity moving through a wire as if it were water flowing through a pipe. Seriously, if you can get this one idea down, everything else is going to click into place. It's the key.
All right, let's get into the building blocks. There are three big ones you absolutely have to know: voltage, current, and power. These are the core ingredients for every electrical circuit out there, from the flashlight in your drawer all the way up to the entire national power grid. First up, we've got voltage. Now, going back to our water pipe analogy, voltage is basically the pressure. It's the force, the push, that gets those electrons moving in the first place. The higher the voltage, the stronger the push. Pretty simple, right? To give you a real-world example, a standard outlet in a home in Italy has about 230 volts of push. Okay, so if voltage is the pressure, what's current? Well, current is the actual flow. It's how much water, or in our case, how many electrons are actually moving through that pipe. We measure it in amperes, or just amps for short. So let's keep it simple. Voltage is the push, and current is the flow. Now, just to give you an idea of the scale we're talking about here, check out this number. A single amp of current, just 1 amp, means that over 6 quintillion electrons are zipping past a single point in that wire every single second. It's just a mind-boggling amount of stuff moving around that we can't even see. So what happens when you put the push and the flow together? Well, you get power. And power is what actually does the work, right? It's what makes a light bulb bright or a motor spin. And the math is super easy. You just take the push, which is voltage, you multiply it by the flow, which is current, and boom, you get power, which we measure in watts.
Let's make this super concrete. Imagine you have a little lamp that runs on 12 volts, and let's say it's using 2 amps of current. What's its power? Simple. 12 volts times 2 amps equals 24 watts. That's it. It really is that straightforward.
Okay, so we've got the basics down. But there's another really important piece to the puzzle. Turns out, electricity isn't just one thing. It comes in 2 different flavors, and they power our world in totally different ways. We're talking about alternating current and direct current.
First up, let's talk about direct current, or DC. This one is pretty easy to picture. The electrons are on a one-way street. They just flow steadily in one single direction. Think of it like water pouring out of a tank through a hose. Just a nice, constant, stable flow. Simple.
And then you have alternating current, or AC. And this is where things get interesting. Instead of a one-way street, the electrons are constantly moving back and forth, reversing direction over and over again, super fast. The flow kind of oscillates, like the tide coming in and going out. This constant back and forth actually creates a wave pattern, a sine wave to be exact.
So you might be thinking, okay, why complicate things? Why do we even need 2 different types? Well, the answer is that they each have very different strengths and weaknesses, and understanding that difference is key to understanding, our entire modern electrical world. Let's break it down. The really big deal with AC is that you can change its voltage super easily with something called a transformer. This makes it amazing for sending huge amounts of power over really long distances. DC, on the other hand, is the king of batteries and electronics. All your gadgets, your phone, your laptop, they need that steady, one-way flow that DC provides. So where do you find AC in the wild? Everywhere. It's the workhorse of our power grid. It's what's coming out of the outlets in your wall right now. It's powering our homes, our cities, giant factories, and all those heavy-duty appliances like your fridge and your AC.
And DC? Well, DC is all about portability and storage. Think about it. Your smartphone, your laptop, even electric cars, they all run on DC power stored in batteries. Solar panels, they generate DC power straight from the sun. Here's a super simple rule of thumb. If it has a battery, it's a DC world.
Okay, but let's dive back into AC for just a second, because not all AC is created equal.
There's actually a pretty important difference between the kind of power that goes to your house and the kind that goes to a giant factory. Let me show you what I mean.
See, most of our homes run on what's called single-phase AC. It uses 2 wires, and it's perfect for everyday stuff like your lights and your TV. But big industrial plants with heavy machinery or those super-fast EV chargers, they need way more juice and a much more stable supply. That's where 3-phase AC comes in. It uses 4 wires to deliver a much beefier, more consistent flow of power.
Okay, so we've gone through voltage, current, AC, and DC, the whole shebang. But why does any of this matter? What's the big takeaway here?
Really, it all boils down to this. AC and DC aren't enemies, they're partners. Think of AC as the long-haul trucker of electricity. It's fantastic at getting massive amounts of power across the country to our cities and homes. And DC is the specialist. It's perfect for the precise, delicate work of running your smartphone or storing energy from the sun. They need each other.
And that leaves us with a really interesting question for the future. You know, our whole modern world was built on an AC grid. But think about what's happening now. We've got solar panels generating DC, batteries storing DC, and electric cars running on DC. So you have to wonder, is the balance starting to shift? Are we maybe, just maybe, entering a new DC era? Something to chew on. Thanks for joining me.